In our next segment, I'd like to acknowledge and highlight the various research centres, pillars and clusters that are showcasing today. As a research-intensive university, SUTD will ensure that its research is relevant to and has an impact on lives and society. Ideas and concepts will be developed and translated into products, enterprises or policies, which will have concrete benefits for Singapore and Singaporeans, such as the creation of new jobs, improving Singapore's position in the global knowledge economy, or informing national policy making. These efforts will in turn build a multidisciplinary research community with an open and collaborative culture that will also advance knowledge in technology and design. By clicking on the links on the First Industry Workshop website, you'll have an overview of SUTD's research centres, pillars and clusters, and their research capabilities. Next, we are showcasing SUTD research projects by faculty from our SUTD research centres, pillars and clusters. You may also find out more about these research projects from the SUTD website using our QR code or click on the link in our webinar.
Transportation is responsible for a quarter of the world's global CO2 emissions. This is a greenhouse gas that contributes to global warming. About 3/4 of that is due to road transport. This means the cars and trucks that we use to get our goods and to move around. The world vehicle population is about 1.3 billion vehicles today, and it's expected to grow to 2 billion vehicles by year 2050. Freight transport demand is expected to grow 3 times around the same time frame. So the challenge is really how to address this growth in demand. How can we make sure that we fulfill these travel needs sustainably? So my research at SUTD looks at sustainable urban mobility. We are interested in different ways to reduce the environmental impact of transport in our city. One of the most recent projects we did was to look at freight transport or the movement of goods in the city. And we're thinking of different ways to optimize the movement. So one thing we found out through the research study was that trucks actually idle quite a fair bit and also are not fully loaded most of the time, and these are signs of inefficiencies that we're trying to correct. There are several things that we can do as an individual to reduce the environmental impact of transport. First is to avoid car travel wherever possible. So this means adopting virtual meetings instead of physical meetings, or walking, cycling and taking public transport like the bus or MRT. If we were to take taxi or private hire rides, we can consider sharing the rides. The average car occupancy is only about 1.7 passengers, which is fairly low. A car can actually take on more passengers, so share the ride when you can. Another thing we can do if we were to opt for car travel is to consider using smaller or lighter vehicles that's more efficient than bigger and heavier ones, or even consider the use of hybrid vehicles, which are more efficient. In terms of online shopping, consumers can also make a difference by choosing maybe not so urgent deliveries or having their deliveries sent to delivery lockers. So this reduces the risk of missed deliveries and extra trips that have to happen. So small choices like that can actually make a difference as well.
We are constantly talking about the rising levels of the ocean, and us being within an island, we need to think about which futures we will be inhabiting and how to design for those futures. A future where the water has risen so much that the new structures need to float within the water in order for the kind of community to be able to migrate towards this island. Our research lab is called Form Actions. It is based in SUTD. We have used the topic of interest in Form Actions to also develop the work with the students in the various option studios, always regarding an exploration of the oceans and the condition that the oceans will provide us in say 100 years through all the climate crisis that we are very much discussing right now. The Shenzhen Hong Kong Biennale is of particular importance for SUTD because this particular biennale is called The Eyes of the City and is about the inclusion of new technologies into the way in which we live, and within those there is one particular district that has a topic that is about water. So I think it's a very appropriate place for our school to be embedded into it, in this kind of a conversation. The big task of the design was how to include in it models of different scales, of different optional studios, AR, VR, and also videos and projections. And so we created a big plinth, which is about 180 square meters. Is almost like a floating, very sculptural piece that cantilevers, and it has recesses for all the models. The piece is completely painted in black because the space is also be darked out. So the idea is that all the models will feel almost like floating within the space. It really pushes us to think about architecture and architectural design, urban design, not as being now and here, but it kind of requests from us that we think about a future.
Many people are concerned about recycling in Singapore today. I think one of the main reasons is people see that the landfill on Semakau will be full very soon in 2035, and they're worried about that. However, what people are often less aware about is the role the informal sector plays in recycling. And some statistics show that informal recyclers, which includes karanguni and charities, collect as much as 90% of the waste recycled by households. At the same time, we've found in our own social research that the informal sector is facing different kinds of challenges today. One area is because of changes in the built environment, it's difficult for karanguni to connect with households. Also because of people's changing work schedules when they're at home. So we took that insight from our research and tried to put that into a design project to look at how we could utilize technology to redesign the informal sector rather than the way that technology is often used, which is to disrupt or displace traditional systems like this. From that design research project, we developed an app for smartphones, which we called Honk. We then piloted the app in 3 neighborhoods in Singapore with over 200 users and 3 karanguni. From that, we found a new series of challenges that were unexpected for us. In particular, we found that karanguni rely on various ways of aggregating materials, and our app did not provide that. So what we're looking at now is how to combine aggregation with the app, either through something like a smart bin system or through social institutions like maybe a neighborhood committee.
Some people may feel that the flipped classroom may not be such a good idea because you are unable to consult the prof in real time whenever you're in doubt.
It's mostly us learning by ourselves without much guidance from our professors.
Some students might think that there's no class, I can just watch the video at home.
Since it's learning on our end and we still have school, we kind of take it as something extra, like extra work for us to do.
Flipped classroom means that you're actually bringing some of this learning back to the students. We transform an hour of actual physical lecture into a flipped classroom. And this is usually done in a way that it is a pre-activity. So the students are expected to learn certain concepts through the lesson material online, outside of classroom, before they come to the classroom. And when they come to the classroom, these concepts will be further explored and applied in the classroom. Having spent more than a decade doing actual physical lab research, right? So this was my research in bone tissue engineering. When I switched fields, now that I'm a lecturer and I went to class, somehow the passion for research was still in me, which is why I decided to embark on a full-on research, pedagogical investigation about the effectiveness of the flipped classroom. From the research that we did at SUTD in 2015, this was just a flipped classroom model but without peer instruction. So I didn't have the assessment component, neither did we have the peer-to-peer discussion. And we found that it didn't work so well. And so in the following year, and this is after the talk by Eric Mazur, we decided that we will try putting in some things that he has said. And so this quiz, peer-to-peer discussion and a quiz again, reduced the anxiety that the students felt. They actually looked forward to learning, and we find that from our experimental results, 80% of them received a full score for the second quiz, which means that the peer-to-peer discussion really made a significant difference and that they learned very well from each other. Many institutes have tried flipped classroom, but sadly all they do is they throw in some videos and then maybe a quiz. And so for our students at SUTD, for the flipped classroom, they actually have, I would like to call it a package, a flipped classroom package, where they get the video recordings, the PowerPoint slides, as well as a keyword list. When we actually prepare flipped classroom lesson material, we take many things into consideration. So for example, we ensure that we break each lecture into maybe 4 to 5 mini lectures, which are about 10 to 15 minutes long. The other thing that we've included is this thing called concept quiz. So every time a concept is taught, so at the end of every mini lecture, there are a few questions that directly assess the learning objective. Because we've been testing them on a weekly basis, that by the time it comes to the exam, right, they are maybe desensitized, or you can say completely prepared. We did see an increase in exam scores that was significant over the years after the implementation of flipped classroom with peer instruction. We also saw that the students were punctual for class because we made sure that the quizzes were, it starts at the beginning of class. They were actually present, right? So that helps with absenteeism as well. So the rationale for designing a flipped classroom is really the fact that we wanted to push some of the learning back to the students. We want them to have this self-directed learning skill. Every time we run this course, we actually collect feedback to make this learning experience better for the students. One of the things that we are also exploring is to see if we can use certain gamified lab simulations. So we are interested to see how we can use this or even games as a pre-activity, which I'm sure the students will find fun and engaging.
For flipped classroom, the e-learning, you are able to digest the information at your own pace.
It encourages self-learning.
I feel that flipped classroom is actually a good idea because it allowed us to go back and check all those concepts that we couldn't catch in class.
We produce 300 million tons of plastic every year, and 90% is actually missed, it's not recovered. It ends in oceans or ends in landfills. Plastic per se is not bad. I mean, plastic was invented in the 1930s, and since then, actually, most of our development, in the last century cannot be understood without the benefits that plastic brought into society. The problem is actually also how society has become added to this material and the amount that we are producing and this lack of integration into the natural systems. We are not trying to remove plastic. We are not trying to go back 100 years on technology. What we are trying is completely the opposite. What we are trying to do is to bring materials that are they outperform plastic in many senses. They open like new possibilities, and they enable to make engineering in a society that moves around biology, and by definition that society will be sustainable. So take, for example, the case of FLAM, right? The material that we made in collaboration with Stilianos. So this material is not only strong, but again, since we never modify the composition, like respect the natural molecules, it's actually perfectly integrated in the ecology of Earth. So FLAM is made out of cellulose and chitin. They are like the most abundant and second most abundant organic polymers on Earth. Cellulose is well known for everybody, is everywhere in green plants, right? Chitin is less known because of the lack of industrial uses. Chitin, for example, is the cells of the insects. The protective exoskeleton of the insect is made mostly of chitins. Same thing for molluscus and the sea cells. Actually, they are also made of chitin. So it's a molecule that nature is using in very different areas to make strong protective materials. In the Fermat lab, the lab that I lead in SUTD, we focus on the integration of biology in other engineering fields. We are setting the ground to what we call the biomaterial age, where biology will link and integrate with other engineering fields to bring them to the next level. In the case of plastic, what we are determined is to actually break this cycle of production and consumption of plastic in a non-sustainable way. And what we're trying to do is to set a new paradigm that is based on biological materials, where your materials are produced, manufactured into products, and degrade in closed regional areas. And actually they have like this kind of circular economy society embedded into the material itself.
I like hawker centre because I like to hang out with my friends and my family.
We like hawker centres because it's affordable and there's a wide variety of food available there.
I like the hawker centre because of the local kopi.
I like hawker centres because of the food that gets passed down generation to generation through their recipes.
In Singapore, food is very important, and hawker centers is the place where people celebrate food in community. So we think this is a subject of study for us, and we think that the hawker centers could be further explored and incorporate new things to make them more exciting and more relevant in the future. Hawker centers now are under the pressure of the food courts and the malls. So the question would be, how can we make them relevant again? How can we incorporate new things? How can we change and tweak the existing spaces so that they are relevant and attractive for people and to face the new challenges that Singapore is undergoing? So part of the research I'm doing in SUTD is related to sustainable space making by using digital tools. So digital tools for architecture is the way that we can integrate data with design intentions. So we can merge very objective information with our intuition to really create sustainable spaces. So we can actually design geometries that are self-shaded and create cross-ventilation that are utilizing more our resources, natural resources and energy, and to address more complex challenges. The challenges in the future, I think, would make the hawker centers be more integrated and articulated with society. So it's not a room where people go, it's more a space that is more connected, more open, and also more sustainable. So I see the hawker centers like something closer to a park than a room within a building.
The aviation industry has been one of the fastest growing industries in the world for the past 20 to 30 years. This trend was suddenly interrupted by the COVID pandemic, which almost stopped air transport activity all over the world. Until recently, congestion was the major concern in airports. Right now, congestion is no longer a concern for the airports because they are operating under very low utilization rates. This does not mean, however, that aviation research has stopped. In fact, we are going through a very critical moment that is going to reshape the way that airports plan their operations. My research team works mostly on the development of research on airfield and airspace demand management. This field of research aims to investigate how to balance demand and supply in order to operate better flights and more efficiently. To give you an example, airport schedules has been built over many years through a system of historical precedents called airport slot allocation. According to this system, airlines need to request slots to an airline in order to operate their flights at specific times of the day. However, once an airline receives one of these slots, this airline can keep that slot forever, provided that operates those flights at acceptable levels of delays and without match cancellations. The advantage of this system is that it gives some stability to the airports and the airlines that in the long term are not threatened every year by significant changes. On the other hand, this system has also been highly criticized because in the long term, airport slots become unavailable and airports does not have the flexibility to accommodate new flights and new market opportunities. In my research, we developed tools that combine machine learning and optimization models in order to support airports understanding airport demand patterns and passenger choices, and then help them designing better schedules that will take into account considerations related to airport connectivity, competition between different airports, and airport-specific constraints such as airfield capacity or environmental impacts. For instance, if a flight needs to be rescheduled, airports tend to apply a more manual approach to shift the flights around. Take for instance the Kangaroo route, which is a very popular route that connects passengers from London to Sydney in Singapore. If you need to displace one of these flights, for instance from Singapore to Sydney, then the passengers that come from London might have seen their connections disrupted. What we propose instead is a tool that leverages machine learning to optimize this process. Right now, the future of aviation is very uncertain, and nobody exactly knows what is going to happen in the next few years. What is clear to us is that sooner or later, we will fly again. And those airports or aviation agents that will be more prepared for the recovery will likely dominate the skies for the next few years. Therefore, having tools that allow us to quickly simulate different scenarios of operations will be critical given the uncertainties that we are going through. The Aviation Studies Institute is working on the development of these tools in collaboration with our industrial partners. We believe that these tools can help airports understanding better their capabilities and support them designing better schedules that will eventually lead to fewer delays in the airports, better passenger connectivity, and more sustainable operations.
I work in a new area in robotics that is called soft robotics. It's been in development for the last 10 years. And the main goal of soft robotics is to develop new and better hardware for robotics. Most of the state-of-the-art in robotics right now has improved in performance regarding controls, software. But if you look at the hardware that robots currently use, it's the same type of hardware that we have been using for the last 50 years. That limits the functionality of robots. So one of the main drivers of soft robotics, which combines the use of materials, chemistry, and advanced fabrication, is exactly that, to advance the state-of-the-art of functionality in hardware for robotics. So for example, in traditional robotics, we normally design individual components and then we assemble them. In soft robotics, one of the major advantages is that we can co-fabricate an entire system. For example, this soft finger for a soft gripper has an internal structure that is made of a stiffer material, has a skin wrapped around it. In the top surface, we have a flex sensor. All these can be fabricated in one go with our 3D printers, right? This is a robot that mimics a stingray. They have hundreds of little bony structures that are called lepidotrichia. And of course, if you were to build a robot to replicate exactly that, it will be a very complex robot. Instead, what we do is we only have one actuator per fin, but we tailor make the rest of the fin to have the right material distributions so that it will oscillate, mimicking the motions of a real stingray fin. The challenge is that the material properties of these structures, again, are non-linear and time-dependent. So traditional modeling approaches don't work very well. So we need to often resort to data analytics or machine learning, for example, to have a more accurate set of models. The challenges of modeling also affect fabrication. All of the fabrication done in the lab is, again, built in-house. We make our own printers because printers that are capable of handling this range of materials are not available commercially now. We have many industrial applications that cannot be tackled by traditional robotics because the hardware is not capable of performing under those environments or under the requirements of the task. For example, logistics, right? Nowadays, people order everything online. Here in Singapore, Red Mart, and people order a high mix of items. Your order can have some cereal, fruit, vegetables, rice, etc. Soft grippers, for example, are ideal for this type of applications because they can handle this high mixed low volume set of items. Another area where we can use soft robotics is in manual operations in harsh environments. These are tasks where humans have to do repetitive, dangerous tasks that require high dexterity. One area that we still haven't explored, but we are really keen on moving to, is the use of soft robotics in wearables, in particular for the elderly population here in Singapore. Soft robots, unlike traditional robots, are inherently safe to be used around humans, right? So this lends to ideal applications where we have, for example, wearables that can be used for therapeutic applications, for example, for joint care or posture care. They can also be used in therapy at home to alleviate some of the loads in hospitals. It's an area that has many interesting, challenging research questions to be solved, but also that we see as having very good potential, in particular here in Singapore.
So people need three things to survive on Earth: food, energy, and water. In our research group, we are targeting two of these fundamental challenges: water and energy. And we want to use low-dimensional nanomaterial to solve these two challenging issues together. Usually, in the research community, some research group, they are targeting on solving energy issues, and some group, they are working on water treatment. However, in SUTD, we are focusing on one very unique area. We are trying to find one solution for these two challenging issues together. So in one of our projects, it's called the desalination battery. Basically, we desalinate seawater, ocean water, remove the sodium and chloride ions from the seawater. At the same time, we utilize the sodium and chloride ions to store energy. So we desalinate the water and store energy, making that two steps together. With these new solutions, actually we can supply fresh seawater, desalinated water to everybody in Singapore. At the same time, we can have low price energy storage being available to everybody. My big vision for this project is we can turn the entire ocean into a big desalination battery, a huge desalination battery, so everybody can enjoy the desalinated water and free power from this huge desalination battery. We are also looking at to recycle valuable resource from the seawater. For example, as we all know, lithium metals is one of the natural metal we can find in seawater. We're also looking at ocean mining to recycle those very valuable metal ions from seawater and then utilize them as battery electrode to store battery or for other purpose. I think by that way, we can maximize the natural resource we can achieve from the ocean.
Advances in material science often lead to huge increases in productivity and advancements in society. If you think about it, it's like the Stone Age Bronze Age, Iron Age, they're all named after materials. And more recently, silicon and glass optical fiber led to the computer and the internet. So you can see that these technologies have had a profound impact on the way that humans live and behave, and also fueled the economy to a certain extent. And therefore, it's very important that we continue to design, discover and develop new materials. So we're studying chalcogenide materials. These are materials that substantially consist of sulfur, selenium and tellurium, and they have fascinating properties. One of the properties I like and study the most is their phase change property. So they can exist in multiple states at room temperature. This is very different to most materials. Here we have an opportunity to switch them and use those to make devices that have switchable properties. So you might have experienced chalcogenides, especially if you're my age, when we were recording most of our data onto DVDs and CDs. They were actually the active layer in the rewritable CDs in the 90s and noughties. These materials have a number of applications aside from the technological applications that we're looking at in Actalab. For instance, chalcogenides are often used in solar cells, and they're used in thermoelectrics, also semiconductor devices as well. So in our group, we're moving away from some of the more traditional chalcogenide materials that other groups are looking at for data storage, and rethinking some materials that were once discarded for data storage applications and applying them to photonics. One of the big advantages of our group is that we can go through the whole process from conceiving an idea for a material, simulating it, testing it in the lab, or trying to create it and test it in the lab, and then fabricating a device. So we don't only do device design and we don't only do materials design, we do the two things in conjunction, and this gives us an extra degree of freedom because we're no longer limited by off-the-shelf materials or pre-existing designs. We can design the materials and design the devices synchronously for a specific application. We've recently found a material that has a very high transmissivity in the visible spectrum, and this is really useful for display technologies. We're currently working with A-Star, other universities in Singapore, to create holographic displays and beam steering devices based on these materials. And hopefully one day we'll all have a chalcogenide holographic display in our living rooms.
Once again, a huge shout out to the generosity of all our sponsors. Our deepest appreciation for their strong support for the first Industry Workshop 2022. On behalf of the first Industry Workshop 2022 Organizing Committee, I would like to extend our deepest gratitude for your participation in making this event a success. It has been an interesting day filled with visions for innovation and collaborations for the future. My name is Wayne, and it has been my pleasure to host you for the first Industry Workshop 2022. Thank you for joining us, and stay safe.